In Chapter 4, we're going to take a look at probability, random variables, and probability distributions. In Section 1, we're going to start with some basic probability rules. So probability deals with randomness. So rock, paper, scissors, coin tosses, the lottery, casinos, games involving dice, spinners, or cards, all of those involve randomness. Even traits we inherit, such as gender, hair and eye color, blood type, dimples, are all determined by the chance involved in which genes get passed along. All of these represent chance behavior that we can understand and work with. The outcomes are governed by chance, but in many repetitions, a pattern emerges. And we use mathematics to understand the regular patterns of chance behavior, which is called probability. So for the definition of probability, we say chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. There are two types of probability to describe chance. Empirical probability and theoretical probability. So empirical probability is based on actual observations. If you flip a coin 500 times and you get heads 489 times, the empirical probability is 489 out of 500. Theoretical probability is empirical probability based on an infinite number of trials. So for example, we'd expect that out of an infinite number of flips, half of them, when you flip a coin, should land on heads. So the theoretical probability is 0.5. So every event that has randomness has an empirical probability and a theoretical probability. So there are some important terms that you need to know when it comes to probability. The first one is a random event, which is an activity with a measurable result. So in the example we just looked at with the coin, our random event was flipping the coin. The coin was in the activity, the measurable result were the number of heads we got. Outcome is the result of one trial of one random event. So if you flip a coin one time and you get heads, that outcome is heads. An event is a set of related outcomes. So my event for that coin flipping is 489. All 489 flips would be my event. And then all of the flips that came out heads would be my event. And then the sample space is the set of all possible outcomes, which we usually denote S equals, and then we use curvy brackets around our sample space. We usually list all of the possible outcomes inside those brackets. So like flipping a coin, all of our possible outcomes are heads or tails. So my sample space is heads and tails. So we all know that the probability of flipping a coin and getting heads is 1/2, and the same with tails. So the probability of an event is the number of outcomes in the event divided by the number of outcomes in the sample space. So the way we write that, we can say the probability of our event, which I'll denote E, is the number of outcomes in event over the sample space, which is how we get 1/2 for a coin, flipping heads, because there is one outcome that results in heads, and the sample space has a total of 2 outcomes, which gives us 1/2. In this formula, though, all of the outcomes in the sample space must be equally likely. And most of the probability we look at are going to be that way. We're not going to look at probabilities where you have a trick coin where heads has more than a 50% chance of occurring. So let's look at some examples. So we have a bag that contains 10 marbles, 2 black, 3 blue, 1 red, and 4 white. We want to find the following probabilities. So we want to find the probability of pulling out a black marble. So I know my denominator is going to be a 10 because there's a total, my sample space is 10 marbles. My numerator is the number of black, which is 2. And if all possible, we always want to simplify our fractions. We get 1/5. Now the probability of pulling out a red marble. So again, denominator is 10, and there's only 1 red marble, so 1 out of 10. Our second example says 2 dice are rolled and the sum of the pips is noted. The dots on a dice are actually called pips. What is the probability that a sum of 9 is rolled? Now this is a little bit different because it's not asking you what's the probability you roll 2 dice and you get a 9. It's asking that if you roll 2 dice and you add the numbers on those dice, you get a 9. So we're going to create a little table. Okay, so we have dice 1 across the top, and we'll put dice 2 along the side. Oh, I wrote 2. Okay, so we have the possible outcomes we can get for each of our dice across the top and the bottom. And then we are going to, in each box, put their sum. So if I roll 2 ones, I'm going to get a sum of 2. If I roll 1 and 2, I'll get a 3. A 1 and a 3, I'll get 4. 1 and 4, 5, 6, 7. And then 2 and 1, 3, then 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and then 7, 8, 9, 10, 11, 12. This is going to become a very important table. A lot of the probabilities that we are going to do have to do with the probability of rolling a specific sum of 2 dice. So this is a really important table, and we're going to see it again in just a little bit. So now I want to account for all of the times a 9 appeared. So if I look at my table, I have 1, 2, 3, 4 9s. So the probability you get a sum of 9 is 4 over my number of outcomes, which in this case there are 36. And 4 out of 36 is 1/9. The next example has to do with flipping a coin. So a coin is flipped 3 times, and the results of each flip are noted. We want to find the probability that exactly one of the flips results in heads. So I'm going to go ahead and list all of the outcomes for flipping 3 coins. So we can get 3 heads, 3 tails. Now, the different orders in which we get like 2 heads and a tail are considered different outcomes. So heads, heads, tails, heads, tails, heads, and tails, heads, heads are different outcomes. Okay. Then we have tails, tails, heads, tails, head, tails, heads, ooh, that's not an H, heads, tails, tails. So there are a total of 8 outcomes. Okay. So out of our 8 outcomes, we want the number that had exactly 1 heads. So that was tails, tails, heads, tails, heads, tails, and heads, tails, tails. So 3 out of 8. Okay. The next question asks, what's the probability that at least one of the flips? So that's the probability at least 1 head. So out of our 8 outcomes, there's only 1 time that we don't get at least 1 head, and that's when we had 3 tails. So 7 out of 8. So when we talk probability, the probability of any outcome of a chance process is a number between 0 and 1. That describes the proportion of times the outcome would occur in a very long series of repetitions. So 0 obviously here represents never happens. And 1 would represent always happens. And we will do examples where the probability is 0 or 1. Okay? The idea of probability seems straightforward. It answers the question, what would happen if I did this many times? So randomness is predictable in the long run. So all of these probabilities we have, someone did hundreds of trials to figure out that in the long run, the probability of flipping a coin that is evenly weighted is 50 out of 50. But our intuition about randomness tries to tell us that random phenomena should also be predictable in the short run, which is what we're going to take a look at next. So there is a myth it's the myth of short run regularity. So what it says is that even though the probability that randomness is predictable in the long run, it does not allow us to make short run predictions, which is where we get the law of averages, which is something that people use all the time but it's not actually accurate. So future outcomes are not affected by past behavior. So women have a 50% chance of having a boy with each pregnancy. The gender of any previous children does not matter. It works the same way with girls. So that's why you can get families with 5 girls or 5 boys or 3. You can get families with multiple children because it doesn't matter if their first 2 children were boys. Each pregnancy has a 50% chance. It also works the same way with flipping coins. Like, we know that in the long run, overall there's a 50% chance that a coin will come up heads. But I could flip a coin 10 times and get heads 10 times in a row. So every time you say, well, they're due a win or do something because they've already lost so many times or whatever, that's where the myth of law of averages comes into play. So basic rules for probability. Probability of any event is a number between 0 and 1. Probability of an event is the long run proportion of repetitions on which the event occurs. All possible outcomes together must have probabilities that add up to 1. So if you take all of the probabilities for a sample space for each individual event, add them all together, you'll get 1. The probability that an event does not occur is written as 1 minus the probability the event does occur. So if I want to know what's the probability of not flipping heads, it'd be 1 minus the probability you do. So when we refer to the event not A or an event not happening, it's called the complement, and we put a little exponent C. So a little rule here. So the probability of event A is 1 minus the probability of not A. Or you can think of the probability of not A being 1 minus the probability of A. Or we know that the probability of A and the probability of not A have to add to 1. So all of these statements mean the exact same thing. Mutually exclusive is another big thing in probability. So if 2 events have no outcomes in common, their probability that one or the other occurs is the sum of their individual probabilities. So if 2 events have no outcomes in common, we refer to them as mutually exclusive or disjoints. So in other words, the probability of A and B is 0. So they cannot occur at the same time. So the probability of flipping heads and tails is 0. I can't flip a coin and have it land on heads and tails at the same time, no matter what people say. So let's use that and our lovely table of outcomes when it comes to rolling 2 dice. So this is a much prettier table. It's got the pictures of the dice. So the red die is our first one, and then the white one is our second one. So imagine rolling 2 fair 6-sided dice, 1 red and 1 white. We want to know the probability of rolling a sum of 5 or 2 even numbers. So in my table, first I'm going to find the ones where we have a sum of 5, which I'm going to highlight green, and then I'm going to do 2 even numbers in yellow. So sum of 5. Well, the only way to add to 5 are 2 and 3 and 1 and 4. So I'm going to find every time I have a 1 and a 4 and a 3 and a 2, which happens 4 times. Okay. The next one is 2 even numbers. So that's 2 and 2, 4 and 4, and 6 and 6. Oh, that's just two even numbers that are the same. There's also 2 and 4, 2 and 6. There's 4 and 2, 4 and 6. Then there's 6 and 2 and 6 and 4. Forgot about those. One thing we noticed though, so this is going to be event A and this is going to be event B, that I did not have any overlap. I highlighted different things. So I can't have my probability of A and B getting a sum of 5 and 2 even numbers does not happen here. These are mutually exclusive events. Which means the probability of getting my two events, there are 4 out of the 36 outcomes that result in a sum of 5, and there are 9 events that give you two even numbers, which gives me a total of 13 out of 36. Which leads us to our general addition rule for mutually exclusive events, which says the probability of A or B, so A or B, is the probability of A plus the probability of B, as long as they're mutually exclusive. We'll talk about if they're not mutually exclusive in a second. Let's look at a couple more examples. So online courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who's taking an online course for credit and record the student's age. Here's the probability model. So we have 4 different age groups, 18 to 23, 24 to 29, 30 to 39, and 40 or over. And then we have the probability that someone will fall within that age group. 0.57, 0.17, 0.14, and 0.12. The first thing we want to do is show that this is a legitimate probability model, which means we want to show that the sum of the probabilities adds to 1. So 0.57 plus 0.17 plus 0.14 plus 0.12, which does equal 1, so yay. Now we want to find the probability that the chosen student is not in the traditional college age group, which is 18 to 23. So we're basically saying find the probability that they're not in A. Because if we let A be the 18 to 23, we're finding the probability that they're not in that, which is 1 minus the probability they are, which is 1 minus 0.57, which is 0.43. That is the easiest way to do this problem. Second option is to add the other 3 together, 0.17 plus 0.14 plus 0.12, which still results in 0.43. Both of these are valid methods for finding the probability. All right, now let's go back to our 2 fair 6-sided dice, 1 red and 1 white. And now we want to find the probability of rolling a sum of 6 or 2 even numbers. So I'm going to let my sum of 6 be event A and my 2 even numbers be event B. So sum of 6. You can do 6 and 1. That's not 6, sorry. 5 and 1. 4 and 2, 3 and 3, 2 and 4, 1 and 5. So notice how sums go diagonal in a table, which makes life very easy. All right, now we want 2 even numbers. So we already did that. The 2 and 2, the 2 and 4, the 2 and 6. Then we have 4 and 2, 4 and 4, 4 and 6. Then 6 and 2, 6 and 4, 6 and 6. Now in this case, I had some overlap, which means I can't just do my regular rule. So my normal rule would say probability of A plus the probability of B. So the probability that you get a sum of 6, so if we look in our diagonal, that was 5. If I just took in my two even numbers, which is 9, but what's happening here is I'm counting some of the events twice, because there are two outcomes that are two even numbers, which also give me a sum of 6. So what I need to do is subtract the ones that are being counted twice, of which there are 2 of those, which instead of giving me 14 out of 36, is now going to give me 12 out of 36, which can simplify to 1/3. So in this case, my events rolling a sum of 6 or two even numbers were not mutually exclusive. Which leads us to a general addition rule. So if A and B are any two events, then I can say the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Now, if the two events are mutually exclusive, that A and B probability is 0, in which case it's just A plus B. But for when they're not mutually exclusive, then you have to subtract that overlap. So this is the general rule. We can always use it even if we run into mutually exclusive events, because that probability would just be 0. Another very common example that we see in probability are examples that have to do with cards. So here is a picture of a deck of cards. So there are 52 cards in a deck. There are 4 suits. We have clubs, spades, hearts, and diamonds. Okay. Each suit has an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Jokers do not count. So we're going to determine if the following events are mutually exclusive, and then we're going to find the probability. So our first probability is the probability we get a red or a queen. So basically we want to ask ourselves, is there a red queen? And the answer is yes. So these are not mutually exclusive, which I'm going to abbreviate ME, which means I need to take the probability I get a red card, which half the cards in a deck are red. So 26 out of 52, plus the number of queens, which there are 4 of, so 4 out of 52, minus the red queens, of which there are 2. So notice here that even though I know half of them are red, I didn't write it as 1/2 because it's easier for me to add and subtract fractions that have the same denominator. So we're going to do 26 plus 4, which is 30, minus 2 is 28 out of 52, which is 0.54. So sometimes we can write the answers as decimals. This is where you're going to be told in math, decimals are allowed. You can have decimal answers because probability, especially if we're not dealing with nice fractions, like 28 out of 52, what does that mean? So there's a 54% chance, which more people are common, understand that what a 54% chance means. So more than half of the cards are red or queen. My second question is the probability of an ace or a king. Now, these are mutually exclusive. I can't draw a card that is an ace and a king at the same time. So the number of aces, there are 4, plus the number of kings, of which there are 4, which gives us 8 out of 52, which is 0.15. And this probability is the same for any two cards. So I could replace ace and king with 2 and 7, 4 and 9, jack and queen. Literally any two cards have the same probability of 0.15 because there's 4 of everything. Now we want to do the probability you get a queen or an even number. So a queen is what we call a face card. So it's not considered even or odd. So these are mutually exclusive events. They're not the same thing. So there are 4 queens, so 4 out of 52. Now even, 2, 4, 6, 8, and 10 are the even cards. So there are 5 of them, and there are 4 suits, which means 20 out of the 52 cards in a deck are even, which gives us 24 out of 52, which is 0.46. So not quite 50%. Now we're going to do black or odd number. Now these are not mutually exclusive because some black cards are odd numbers. So again, if half the deck is red, half the deck is black. So 26 out of 52 plus odd numbers. Ace, not considered an odd number, and ace is technically considered a face card. Even though it doesn't have a face on it, it is considered a face card. So the only odd numbers are 3, 5, 7, and 9. So there are 4 odd numbers across the 4 suits. So we get 16 out of 52. Now we have to subtract the black odd numbers. So that's 3, 5, 7, and 9 twice, of which there are 8 of them. So 26 plus 8, basically, because 16 minus 8 is 8, which gives us 34 out of 52, which is 0.65. So that was the highest percent out of all of the ones we did. So that's the same probability as red or odd number also has the same probability, mainly because black and red have the same probability. So you can always interchange those, and those will always have the same outcome, whatever you put them with. So again, lots of problems we're going to see with decks of cards and rolling 2 dice. So get very, very comfortable with decks of cards and 2 dice. Our next example says students in an urban school were curious about how many children regularly eat breakfast. They conducted a survey asking, do you eat breakfast on a regular basis? All 595 students in the school responded to the survey, and we have data in a table. So they have eats breakfast regularly and doesn't eat breakfast regularly. And then they have it broken down by male and female, and we have totals. We're also going to be seeing a lot of two-way tables with probability as well. So if we select a student from the school at random, what is the probability that the student is a female? So if we're trying to figure out female, we're going to look at the total number of female students and the total number of students. So probability female, which I'm going to denote as F, is 275 over 595, which is 0.46. Okay. The next question says someone who eats breakfast regularly. So we go to eats breakfast regularly. We go to that total, 300. So probability eats breakfast. So 300 out of 595, which is not exactly 0.5. It's 0.504. Very rarely are we going to go 2 decimals unless it's exact or it doesn't change, because I don't like to put 0.5 unless it's exactly 0.5. So I will on occasion go 3 decimal places in that case. Okay. Next one is probability that you get a female who eats breakfast regularly. So that's the probability of F and eats breakfast. So I'm going to look for where those overlap. So eats breakfast regularly and female. So that's going to be 110 out of 595. Which is 0.18. And then last one, a female or eats breakfast regularly. So probability of female or eats breakfast. Now, we did the work, and we can kind of see from the table, these are not mutually exclusive because my and was not 0. So I'm going to take my probability or female, 275 over 595. I'm going to add the probability you eat breakfast, 300 over 595. And then I'm going to subtract the number who are both, which are 110 over 595. Now, in this case, it didn't happen, but a lot of time, if you forget to subtract the overlap for an or that are for events that are not mutually exclusive, you can run into the probability being over 100%. In this case, 275 plus 300 is not over 100%. It gets it at 575, but there are a lot of cases where when you do that, you get numbers that are over 100%. So 275 plus 300 minus 110 gives us 465 over 595, which is 0.78. Last example. We have hair and eye color of a group of women were measured, and we have the results shown below. So we have hair color of black, brown, red, or blonde, and eye color of brown, blue, hazel, or green. Before I do any problem, I'm going to go through and find the totals because I don't have my totals for any of my columns in rows. So I'm going to find my total that have black hair. It gives me 52, so total. Then brown hair, 143, and then red hair, 37, and then blonde gives me 81. And now I'm going to do it for the eye color. So brown, 122, blue, 114, and then hazel is 46, and lastly green, 31. Now, where these numbers should match is in their total. So this number in this last box, the total in the far bottom right corner, should match going down and going across. So 52 plus 143 plus 37 plus 81 is 313. So I should get the same total from the eye color. So 122 plus 114 plus 46 plus 31. And I do. So I know that I've added my totals correctly. So now I'm going to go ahead and find my two probabilities. So the first one is the probability that she has either red hair or green eyes. So that's the probability of red hair or green eyes. Now, if we look in our table, these are not mutually exclusive. is a value for red hair and green eyes. All right, there's not a 0 there, so I'm going to have to subtract the overlap. So the number with red hair, 37 over 313, plus green eyes, 31 over 313, minus the overlap, which there are 7 out of 313. So 37 plus 31 minus 7 is 61 over 313, which is 0.19. So about 19%. The next one says the probability she has red hair. So probability of red hair and green eyes. So this is just the and. So red hair and green eyes is just the 7 over 313, which is 0.02. Only a 2% chance. Let me know if you have any questions over general probability.